Okay, so let me share my screen. Okay, can you see my screen or not? Can you see my screen?
Yes.
Okay, thank you, thank you. So, so last week we talked about the basic motor sizing calculation, and this week we need to continue it lah before we can go into the motor winding. Before that, I want to ask, is it okay to have a test on the week 7, or you want to have a test on the week 9?
Week 9 maybe.
Week 9. Why you guys have a lot of tests on the week 7? Is it?
Yes, and you did assignment.
Oh, I see. So can we do on week 9, maybe beginning of the week lah? Maybe Monday, Tuesday like this. Is it okay? Is it okay?
Okay, Doctor.
Can I now? But anyway, I will be asked again later on. We discuss again later on. So by right, we need to finish the basic motor sizing calculation by today lah. There's a lot of things to cover today, so maybe we will go a bit faster. Last week, when we stop, guys, last week when we stop? When we stop, like where we stop? Where is it? You still remember or not? Hello? Hello? Where we stop last week? Page 4. Page 4. Hani, sudah habis kan? Page 4 kan? Habis atau baru nak masuk? Habis. Oh, okay, okay. So thank you very much. So we'll go into the RSM and the DS, Anna. So first of all, I think we need to know where is RSM first, huh? Okay. Okay. So this one is a non-overlapping winding, non-overlapping winding, where the winding is coiled in one tooth, huh? Okay. Then the other one is, for example, this is another tooth. Okay. Then another tooth. Oh yeah. Hey, sorry, let's say like this one, So maybe the winding is going inside here, then go to the back, and then come out like this, then come again like this. So it's overlap. This is called overlapping, which is more than one coil span. More than one coil span. It covers one teeth and second two teeth, second teeth. So, and then, yeah, I forgot. So we need to know the name of the variable. So this is theta, angle per slot, we call slot pitch, and then the radius of the TRT, and then we have a radius of the slot bottom. This is the bottom side, and then usually we make it double layer first lah, which is a layer number 1, layer number 2. So we call double layer, and we use the name of A slot 1, A slot 2 on the left hand side and the right hand side. Same as well, if let's say this is a overlapping machine, we have a RT, we also have a RSB, but we need to find the RSM, which means the middle radius, that making the area the same. The A slot 3 and A slot 4 are the same. Then this one we call bottom winding, and then this is a top winding, even though this is located at the bottom side. But when we slot the winding, we will put inside this one to the winding slot first. That's why we call bottom. And then this is the place that we will see after we finish slotting it. Then it will become a top side lah. Nah? So okay, figure 3A and 3B shows the slot area per slot page of a PM machine with a double layer configuration. So double layer, layer 1, layer 2, layer 1, layer 2. If let's say single layer, only one slot like this, which means we only have A slot. We don't have A slot 1 or A slot 2. Nah? Of a non-overlapping and overlapping mining machine. So this is a non-overlapping. This is a overlapping. And then, as can be observed in figure 3A, the total slot area of a non-overlapping winding machine, A slot non-overlapping, is divided into two equal slot areas on the right-hand side and the left-hand side, which are A slot 1 and A slot 2. I think I recorded it again. Okay, I recorded it. Which is A slot 1 and A slot 2 lah, huh? So, okay. So we name it lah, huh, so that we can differentiate it easily. So on the right hand side is A slot 1, on the right hand side, and the left hand side is A slot 2, bottom A slot 3, top A slot 4. Okay. And then meanwhile, for the overlapping winding machine, as illustrated in the figure 3B, the total slot area A slot overlapping is A slot underscore overlapping, which means this one, this total, is equally distributed on the bottom and the top slot, which are A slot 3 and A slot 4, where the radius that you both parts of each winding having the same area for overlapping winding machine, RSM. So this is the equation that we need to use to calculate the RSM. Yeah. How to derive it? Okay, how to derive it? So now imagine we have a motor and this is the winding. A slot overlapping, and then we know that we need to have a RSM. Okay, then this is A slot 3, this is A slot 4. Okay, so we know that A slot 3 must equals to A slot 4. Okay, how to find A slot 3? A slot 3 is, we need to find the whole area of this one. Okay, which is pi r square divided by pi r square minus pi r square. So this one is a RSB. This one is a RSM. Okay, this part is a RSM. So we use a big one minus small one, which means pi r square minus pi r square. The big one is a RSB minus RSM. Okay, and then I divided by the number of slots so that I can get this area. Okay, and then equals to, same as well, we use a big one minus the small one. So pi r square minus pi r square divided by number of slots as well. But which r? RSM is the big one. Then this is the RT, the small one. RT, the small one. So RSM, RT. Okay. So cancel, 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 cancel. Then we move the RSM as here, and then we shift this one to here, which means copy RSB square minus become plus RT square equals to RSM square with 2, because 1 plus another 1, so become 2. Then my RSM square will become, so I take these 2 here. So RSB square plus RT square, I copy first, divide by 2. And then because I have a square right? When I bring here, it becomes square root. So this is how we get the equation. RSM equals to RSB square plus RT square divided by 2. So in the case of the PM machine, this PM machine is non-overlapping machine. RSM is no needed to be calculated. Yeah, RSM only need to be calculated if, let's say, you are designing the overlapping machine. Overlapping machine. Yeah, only here. So this for this one, there's no RSM. Then we want to find the slot depth. Slot depth means this length, or this length, or this length. Slot depth. So slot depth is we use the RSB minus RT, or RSB minus RT will be the slot depth. And then so we take the value from the top. So the total area per slot pitch, A slot, total area per slot pitch, we need to calculate the total area per slot pitch, this one. How to do that? Okay, we want to calculate this one. So if let's say we put in 2D dimension. Oh, sorry. Maybe I should draw like this. Okay. Okay. Then we know that this is WTB. Let's say this is one slot pitch on. Then the problem is we want to calculate this part. Then we know that this one is actually WTB divided by 2. And this one is actually WTB divided by 2. So now we want to calculate what? We want to calculate this A slot here. And how to do that? And then this is one slot pitch. Okay, how to do that is actually same. We use the big one minus small circle, and then we divide one slot. Then we will have this one. So which means, if let's say we want to calculate this part, the yellow part. Okay, yellow part, A slot. Let's say A slot. It is actually pi r square minus pi r square. The big R minus small r. So the big R is RSB. Small r is a RT. And then this is the overall things, right? Overall section like this. But we want to have only one slot. So we divide by number of slot. This is the AS. The yellow color one. Yellow color AS. But the problem is we want to find the winding slot. The winding area is not the total slot A slot, the yellow one. So what we need to do is we still need to minus this part and this part. Okay, so what we need to do is we include again minus. Just now we calculate the DS, right? The slot depth. Okay, and then WTB divide by 2. We times WTB divide by 2, which is here lah. But we have two portions, so we times 2 again. So this is the area of the slot winding. When we cancel this one, so we will have A slot equals to pi RSB square minus RT square divided by an S, and then minus DS times WTB. So we input everything, then we get the value. And then we know that we want to insert the copper. So even though we already calculated the total area of the slot, but still when we want to insert the so-called winding, it couldn't be a full one, which means maybe we can only use up the space like this, and the rest will be the rest part will be the blank space, blank places, same as well here. Maybe I use another color. 1, 2, 3, 1, 2, 3, let's say. Then the rest will be blank. I mean blank spaces. So we just use A slot divided by number of layer times packing factor lah. Which means let's say we have already A slot here, we divide number layer. Since this is 2 layer, we divide by 2. Okay, we divide by 2. The total, then we divide by 2. After that, we need to know how good is the packing factor. We have a Pekali, the coefficient. Usually it's a 40%, which means the copper area only takes up about 40%. The rest will be 60% of the blank spaces. If let's say we use hand to wind ourselves. If let's say we use machine, yes, it may go to 70%. So it's a A slot divided by number of layer times packing factor. Then we get our copper area. So we just proceed by using all the value. Then we have the copper area. And then the number of layer is the layer of the winding. And then PF is the packing factor. Given the diameter of copper wire DW is the area of the A wire. So the number of turns per coil is obtained like this, which means number of turns per coil. Okay, number of turns per coil, which means in this side, how many coil we have? For example, we have 1, 2, 3, 4 coil. For example, so same as well here, we need to use the total area of copper divided by the wire. So for example, now we calculate the A slot, A copper, sorry, A copper maybe like this X. We can then we don't know how much can accommodate the wire. Maybe 1, 2, 3, 4. So we use X divided by area of the wire. Then we will know how many wires we can put inside. So that's why we have a number of turns per coil is actually use the copper area divided by wire size area. Then assume that the rated current of motor is a 10 ampere RMS according to Appendix 1, standard specification of an American wire gauge, AWG, American wire gauge size of the solid round wire. Then AWG 18 is selected. Why we say so is actually like this. We would like to run the motor with a 10 ampere RMS. So have a look on the table. Where is the 10 ampere of RMS? By using let's say 18, 18. Okay. We want to know the ampacity. Yes, we want to know the ampacity, which is maybe either 60, 75, or 90 as our decision. Let's say it run at a 60 degree, and then we choose 10 ampere for here. So we will see that okay, AWG 18 actually is sufficient to run for 10 ampere current. And then we need to know why we need to choose AWG, because we need to know what is the diameter in mm, which is a 1.024 mm. So that's why when we go to so since the ampacity is 10 ampere at 60 degree, where the W is the 1.024 mm, then we by using 20, this one, we will calculate the number of turns per coil. And then we use all the information here. Then we have all. With the copper area and the wire size, we can accommodate about 46 number of turns. So we only choose 46 number of turns. Even though if we want to choose higher also can, it depends. And then the number of turns per coil chosen must be nearest smaller integer to the number of turns per coil in calculation. So for example, this is 46.01, we still choose 46. 46.51, we still choose 46. 46.99, we still choose 46. And then after that, just now we only see the number of turns per coil. Now, after that, we want to choose number of turns per phase. What is the difference between number of turns per coil and number of turns per phase? For example, let's say one motor, okay, they have a winding slot 1, 2, 3, 4, 5, 6, 7, 8. well, this is not good. Maybe I choose another one. Let's say one coil here. This is the phase A. Another coil also is a phase A. Then another coil is a phase A, for example, only lah. So just now what we calculate is actually number of turns per coil. How many turns in this one coil? Then number of turns per phase, number of turns per phase is actually the total turns calculated in phase A. So that's the difference. That's why we use number of turns per coil times number of coil per phase. Okay, this formula, this formula, okay, this formula is like this. Number of turns per phase. Okay, and then we know that we have a number of turns per coil. So how can we get number of turns per phase? So it must be, we need to maintain number of turns. And then we don't want the coil. So I put a coil here. And then I want to maintain a phase. So I maintain a phase. So that coil can be cancelled off. Then we can become number of turns per phase. That is why NTPPH, number of turns per phase, is a number of turns per coil. This one, times number of coil per phase. Something like this. Number of coil per phase. So that we can get the number of turns per phase. And then, okay, this one, we will look into the winding arrangement next week. Next week. So, where the number of coil per phase varying according to the combination of slot and pole number. So, the number of a coil per phase is according to the design. In this motor machine, we usually start from 3-phase and let's say like this is 12 slot and double layer. It must be start like this first. Slot can be changed, but 3-phase and double layer is a must. So it's a 12 slot. First of all, what we need to do is we use a 12 slot times 2 layer, double layer, right? Divide by 3-phase. So we have a 8 slot per phase. 8 slot per phase means in a one motor we need to use 8 slots. For example, this is one slot, 2 slot, 3 slot, 4 slot, 5 slot, 6 slot, 7, 8. Yeah, we need to use like this. But if let's say we want to know how many coil per phase, so we just divide 2 slot per coil, then we have a 4 coil per phase. So how to do that? Okay, so now we need to use an 8 slot to become to wind the winding, and then we need to know how many coil. So from here, 1 coil, 2 coil, 3 coil, 4 coil. So this is the meaning of the 4 coil per phase in one phase. Or we can use the formula to check it. Let's say the top one, 12 slot times layer, and then divide by the phase. Then we will have slot per phase. Layer can be omitted lah. Then after that we use this 8 slot per phase, okay, divide by 2 slot per coil, okay, which means I copy this one, 8 slot per phase times, so I times this one, which is become coil divide by 2 slot. So we can see slot and slot can be cancelled. It become, then 2 become 4. So it become 4 coil per phase. So this is so-called 4 coil per phase. And this is the one, so that 4 coil per phase. So using 21, that is 21, okay. Then we will have a number of turns per phase, which is 184. After that, we want to calculate the fundamental of RMS phase back EMF. So for this motor, we want to run it. Then after we run it, we want to know how good the voltage we can obtain. So before we run it, we can do the calculation first. For example, feedback EMF is actually a harmonic, a lot of harmonic inside. But we're only interested in the fundamental, which is n equals to 1. N equals to 1. I'm not sure, do you still remember about harmonic or not? For example, if let's say we want to uh, build this signal, let's say we want to build this signal. Okay, it starts from n equals to 1. Fundamental maybe is like this. Then when n equals to 2, it is something like 2 cycle. Is it 1, 2? Then when n equals to 3, oh yeah, 3 cycle inside there. Then we add up together. For example, this point, add with this point, add with this point. Then we will have this point. This is so-called harmonic. This is harmonic component. When you add up together, it will come like this. So this one we are not interested, but we will interested in the fundamental, because the fundamental can do a lot of, can determine the performance of the motor, which is the only one useful information that we need. So assuming double layer winding, the winding layout for the three-phase 12-shot tempo field machine can be determined. After the pitch factor KPN and the distribution factor KDN and the winding factor KWN can be calculated like this. So for the pitch factor, winding factor, we call winding factor KWN. I will introduce you in the next chapter. It's not here. This one we directly apply first, which is KWN equals to KPN times KDN. And then how can we get, so we have a lot of harmonic. This is so-called harmonic. After that, we can analyze according to different motors. For this motor, the KPN equation like this and KDN equation like this. Then we just apply here and then times it. And then remember that this must be pole pair. P is a pole pair, which is NP divided by 2. And then phase back EMF PM machine is a 4.44 times F kWn, number of turns per phase, times the flux for slot pitch, per slot pitch. Then to calculate the fundamental of RMS phase back EMF, which is n equals to 1, so the frequency of the machine usually is 50 Hertz, according to the Malaysia standard. So we try to run the motor with 50 Hertz, and then the number of turns per phase can be obtained from 21. This one can be obtained from 21. KWN can be obtained from 22 to 24. Flux slot pitch can be obtained from 3. And then we substitute inside here. Then we will have this value. So for example, EPH RMS N equals to 1. So we use a 4.44 times the frequency of a 50. And then our KWN is like this, and pi, number of slot. Remember this one is in radian, don't use a degree. If let's say you want to use this degree, please take out the radian and then times 180. Then we found that, oh, okay, this motor can give us about 21.6 volt for EMF. And then we will calculate the P output and electromagnetic torque. With a star connected motor, and then the rated phase current I phase RMS is a 10 ampere. Estimate the output power and electromagnetic torque EN. So assume the windage, other losses are neglected, which means we do not consider it, which is too small. The power factor of the PM synchronous machine is always unity. This one also the same. For the PM machine, when it starts without load, which means kita tak bagi dia any beban, then the synchronous machine will always run as a unity. And then the output power and the output torque can be calculated by using this equation. So P out is a 3 times V times I times power factor. Then power output related to the torque is a T equals to times omega, P equals to T times omega. Omega is the angular frequency. So power factor is a cos theta, mechanical angular frequency omega m is a omega e divided by p, which is 2 pi f divided by p lah. Okay, this one, in order to interrelated the electrical to mechanical, we always use times a pole pen. But usually only these three stuff like omega, like theta s, like theta p, we involve this kind of equation, or else very seldom. So when we found this equation, then we input everything, then we calculate it. So we can see that the torque is about 10.31 Newton meter lah. So calculate the phase resistance, copper losses, and motor efficiency. So maybe this one, check. Do you need a break first, guys, before I continue? Or I just continue this last page, almost finished. Hello? Awak tak ada orang, semua pergi mana dah? Last page first, oh, okay. Sure, thank you. How many people? We have 35. Another 60 plus, tak ada orang. Where is the 16 plus? So calculate the phase resistance, copper loss, and the motor efficiency. So when we want to calculate the losses, actually it's come from, we want to calculate the resistance, it's come from R equals to rho L over A lah. Okay, so, right, so more. So if we put a wire, go inside and then go out like this, and then go again, right? So first of all, the line should be from this one, go to the, like this. This is the total length that we need to calculate lah, nah? And then we know that this is LA. This part is LA. The problem is this N winding. Okay, so how to calculate this N winding? We use a 1 plus, let's say we assume X% more than the WTB. When we want to, the first thing is it must be at least this long, which is WTB. But it is not 90 degrees. It must be longer. So when it's longer, we assume that it is X%, X% more. So we just use 1 plus X%, which means 1 is here, plus X% is the extra one. And then we times WTB, we times this one, and then we times number of coil span. Okay, this one is for only non-overlapping winding machine. If overlapping, that's different story. This formula cannot be used if let's say overlap. After that, we want to find the total one. So this is Ln. Ln means we are searching the value from here to here only. So if let's say L total is actually Ln L total L total. So L total is actually we have a La plus Ln. La plus Ln. But we have two sides. This is one side. This is another side. So we times 2. So this is how we get. And then we need to times number of turns per phase. Okay, just now this one is only one coil. Okay, one coil. After that, we need to times number of turns. How many turns it has? So assume the length N1 is 40% more than WTB. Then we after that, we use R equals to rho L over A. So where the D is 1.024 mm. Rho is taken from for the copper. So we taken from the Google search one. Then we insert everything. Know that copper losses is 3I squared. And then we also assume that. So just put inside, then get the value. Okay, so we assume the windage friction losses are negligible. So we know that in order to find efficiency and what is the input? Okay, times 100%. Okay, how to get the input is actually P output plus P loss. And usually our losses is copper losses, windage, stray, something like this. But this one we already ignore. So our losses only P copper. So that's why our formula become P out equals to divided by P out plus copper, then times 100%. This is the efficiency. Huh? Okay or not? So I think we stop for 10 minutes. 10 minutes. And then we come back again. Presentation.